Okay, so let's finish the last part, page 3. So now we are finding our eigenvalue associated with our lambda 2. So remember here is that's lambda 2, right, which was 13, our defective eigenvalue. But again, we have lambda minus, there's two factors, okay? I mean, so technically, right, we have two eigenvalues, thus we need two eigenvectors. But again, we know these are obviously the same, the same number. Okay, so I went ahead and I inserted my 13 into my A minus lambda I matrix, and I obtained this form. And I went ahead and again simplified, right? I divided everything by 12 to get these nice 1, 1 zeros. Similarly, right, divided by negative 18, and then 6 to get my ones and zeros. Because now I have, well, again, you can use this matrix if you want. You're going to get the same relationship. But I have x plus y is equal to 0 here. And this is, I mean, these are all the same, right? XY, 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 right? That's a 1. That looks like an R, but that should be a 1. So basically, X is the opposite of whatever Y is. And there is no Z in this case. So we have, I mean, Z is, it could be anything. So for my first eigen vector, okay, associated with my eigenvalue, okay, so this guy, I'm going to let Z be 1. Again, you can let it be anything you want. I'm going to let it be 1 because 1 is a nice number. Okay, so if Z is 1, right, that's my little Z is 1 there. And then I'm going to let Y be 0 because if Y is 0, then obviously X is 0. So 0, 0, 1 is my column vector, my eigen vector associated with lambda 2 equals 13, which again obviously is just the transpose of this row vector. Now we need another eigen vector since, right, we just did this guy, and again now we need this guy. So again, Z can be anything. So I'm going to let it be 0 again. You know, why not? So there's 0. But I can't let well, not 0 again. I let, oh, it's been a long week. Here I let Z be 1. Here I'm going to let Z be 0. And then I'm going to let Y be 1, right? Because if Y is 1, then we know X is just the opposite, which is negative 1. And again, it's just the transpose of this vector. So here are my two, right, eigenvectors associated again with these two eigenvalues, again, are repeated, our defective root. And again, this is important to find this other one because when we write the general form, we're going to need that other eigenvector. I mean, if we have 3 eigenvalues, even if one's repeated, we need 3 eigenvectors. They need to correspond. So again, the same thing we've been doing. Here's our general form. C1 x1 of t plus C2 x2 of t. And again, our multiplicity here was 2, so I stopped at 2 because one of my eigen vector 13 is unique. It's just gonna give me 2 eigenvalues. So again, we know this is very nice. Let's see, maybe get a different color here. So x1 of t, right, we know is just our eigenvector times e to the lambda t, and times our constant C2, and then v to e to the 13t. And we just substitute, right, our eigen vectors. Right, this was the one we obtained from lambda 1 equals 7 from the very first page. And then again, here's our first eigen vector associated with our 13, and then here is the other one. Again, I have our 13 here and our 13 here. And again, this is just some matrix algebra here. I just multiply in our either coefficients or functions right function which is never going to be 0. And again, add these guys up, and the first row is our first solution, right? The second row is the second solution, and obviously the third row. Hopefully you guys can see that. I kind of wrote that a little bit small, but there is our final solution. If you have any questions, please let me know. Again, the only difference is our repeated root here. And that is the end of number 8 in section 5.6.